Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. So this module we are going to look at some of the software approaches that are used for exploiting instruction level parallelism. So we will see how the compiler can also try to exploit the instruction level parallelism and discuss specifically the techniques of loop unrolling and scheduling which are used by the compiler to exploit instruction level parallelism. Before we go into the details of the software issues, a brief recap of whatever we have done so far with respect to pipelining. So all of you all know that if you are looking at the CPI, the average number of clock cycles per instruction in a pipelined implementation, that is equal to the ideal pipeline CPI, which is 1. Ideally, every clock cycle we want one instruction to finish. So the ideal pipeline CPI is 1. But you definitely have other stalls coming into the pipeline because of different types of hazards. You might have structural hazards, you might have data hazards, and you may have control hazards. Structural hazards come up in the pipeline, occur in the pipeline because of not having enough duplication of resources. You do not have enough functional units which will support different combinations of instructions. You have data hazards because of data dependencies and name dependencies between instructions. You have control hazards because of control dependence, and because of that you can't do certain instructions out of order. So all these will give rise to stalls, and these stalls will try to increase the pipeline CPI of your ideal implementation. So you can't just have an ideal pipeline CPI of 1. All these stalls will try to increase the pipeline CPI. The concept of pipelining itself is a basic form of exploiting instruction level parallelism, because in the case of pipelining we only try to do an overlapping of the execution of various instructions in order to improve performance. So that itself is exploiting instruction level parallelism. And handling all these hazards, structural hazards, data hazards, control hazards. Structural hazards of course will have to be handled at the design stage itself, but data hazards and control hazards we have looked at different techniques for handling them. So for handling all of them, when you are trying to look at exploiting the instruction level parallelism, there are basically two approaches that you can use to exploit the instruction level parallelism. One is the hardware based approaches. All the hardware based approaches like dynamic scheduling, dynamic branch prediction, speculative execution, all of them are hardware based approaches. At the same time, we can also look at the contribution made by the compiler or software based approaches to exploit instruction level parallelism. So the focus of this unit is to concentrate on the software approaches or the compiler approaches to handle instruction level parallelism. So earlier we were relying only on the hardware to help discover and exploit the instruction level parallelism dynamically using different techniques that we've already discussed. Now we look at the software technology that can also be looked at, which will try to identify parallelism statically at compile time, for example in processors like Itanium, and see how instruction level parallelism can be exploited. Now when you are looking at instruction level parallelism, we've already identified the fact that you can't just look at basic blocks. If you are only looking at basic blocks, the number of instructions that you have in a basic block is very limited, and you also know that some of these instructions may be data dependent on each other, which means that whatever type of scheduling you use, however complicated your dynamic scheduler is, there isn't enough parallelism to uncover. So you really won't have any benefit of exploiting the instruction level parallelism because there is no parallelism that exists. So we can't just look at a basic block, and branches are very frequent. You have about 15 to 25% of your instructions being branches. So you can't look at only the basic block. You will have to go beyond the basic block, and you will have to look at instructions beyond the basic block and try to look at exploiting parallelism among them. So now to obtain substantial performance enhancement, we know that we will have to exploit ILP across multiple basic blocks, and a very important component which gives you scope for parallelism are iterative loops. So the simplest of these is the loop level parallelism, which can be exploited among iterations of a different loop. For example, if you have a loop for I is equal to 1 to 100, you are going to just calculate x of I is equal to x of I plus y of I. Then you know that each iteration here is going to be independent. There is no loop carry dependence. Each iteration can be carried out independently. So, these iterations, these iterative loops are a definitive target for exploiting instruction level parallelism. And at the hardware level, when we did dynamic scheduling with speculation and all that, we saw how the dynamic branch predictor can do a dynamic unrolling of the loop. So, that was what we discussed for a dynamic approach or a hardware approach. Now, the same thing can be done statically by the compiler as a loop unrolling process. So, that is what we are going to discuss here. Of course, apart from these two techniques, you can also look at vector architectures which will try to exploit the loop level parallelism, which we will do in a later module. So, determining the instruction dependence is critical to identify loop level parallelism. So, if two instructions are parallel, then it means that they are not dependent in each other. They are independent instructions. They can execute simultaneously in a pipeline. They are not dependent in each other. On the other hand, if you know that two instructions are dependent on each other, they are no longer parallel instructions. They cannot be executed in parallel. So, the sequential order of these instructions will have to be maintained in order to maintain the data flow. So, identifying the dependence among instructions becomes very, very critical when we try to look at loop level parallelism. Now, look at a simple loop here and its assembler equivalent. So, the same loop that we did earlier, where we did an x of I plus x of I plus y of I, where you have to load a data from 0 R1. The first element is loaded into register F0. You add some constant to it. So, F0 and F2 get added up. You put it in a register F4, and the contents of F4 is stored back into your 0 R1 memory location. Now, the same process will have to repeat a number of times. So, the loop maintenance code is indicated by means of your subtract instruction here and a branch or not equal to Z instruction. So, every time you execute the loop, modify your pointer value in R1 so that it is pointing to the next location in memory, and as long as your memory location has not decremented down to a particular value, so branch or not equal to Z, go back and execute the loop. For example, if I have loaded R1 with a value of 80, every time I execute the body of the loop, R1 register is going to get decremented by 8. So, if you execute the loop 10 times, then you know that the branch 10 times it will keep repeating the loop. After that, it would have got decremented down to 0. So, you will come out of the loop. So, this is a simple iterative loop where the body consists of only 3 instructions, but unfortunately each of these instructions is dependent on each other, and then you have 2 instructions which forms the loop maintenance code. With 3 instructions forming the body of the loop and all these 3 instructions dependent on each other, obviously you will understand the need for looking at other methods of exploiting parallelism, ILP. So, these 3 instructions, all of them are dependent on each other. You do not have any scope for exploiting parallelism here. So, we definitely have to exploit parallelism only by looking at different iterations of the loop, because different iterations of the loop are independent. So, there is no loop carry dependence here. The iterations of the loop are independent. They are a very good source for exploiting loop level parallelism. So, what are the hazards that we will have to look at here? So, identify the fact that there is a data dependence between the first instruction and the second instruction, which might give rise to a raw hazard. There is a data dependence between the second instruction and the third instruction, which will again give rise to a data hazard. There is a data dependence between your subtract and a branch or not equal to instruction also, which will again may give rise to a raw hazard if not handled properly. So, let us assume for our discussion purposes these latencies. So, between a floating point ALU operation and another floating point ALU operation that is going to use its result, let us assume that you need a latency of 3 clock cycles. Between a floating point ALU operation and a store operation dependent on that data, let us assume that you need a latency of 2. Between load double and a subsequent load use instruction ALU operation, it requires a latency of 1, and a load and a store, there is no latency. Let us assume these latencies for our discussion purposes. And an integer operation and an integer operation, of course, because the execution takes only 1 clock cycle, you do not have any latency. Now suppose if we look at the instructions, the loop that we already showed, if you look at that loop and if you are supposed to schedule the instructions in that loop, this is how you can schedule the instruction. You have the load instruction which loads the first data. Of course, between load and add, I need to have one latency. So the add instruction, there is a data dependency, so you cannot schedule the instruction immediately. You need to have a stall between these two instructions. Then you have the add instruction coming in. Between add and store, again I need to have a latency of 2. So you have 2 stalls between these two instructions. Then you have the store instruction. And then you have the subtract instruction. Subtract and branch are again related to each other. There is a data dependence. So I need to have a stall between the subtract and the branch. And the branch, if you don't assume a branch delay slot, if you assume that the branch takes 1 clock cycle to resolve, then you need a stall after that also. So this shows you the schedule for one iteration of the loop without doing any optimizations. We have not done anything here. You are just looking at sequencing, scheduling the instructions according to the sequence that is given. So you find that one iteration of the loop takes 10 clock cycles to execute. Now can we do something in order to optimize this code and reduce the number of stalls? A simple optimization that the compiler can try to do is scheduling the loop, do a better scheduling of the loop so that your stalls get minimized. So what we have done here in this reorganized code is that your subtract instruction has been moved in the slot between your load and add. We already had a stall between load and add, so that stall is filled up with your subtract instruction. So you are removing one stall. And again your branch instruction and because you had a dependence between the sub and the branch and sub has already been moved forward, that stall is again removed, and the store instruction has been moved into the branch delay slot. So this definitely, just by doing a reorganization of the code, we find that we've come up with a better schedule of the instructions with the stalls getting reduced. So earlier we had 3 stalls or 4 stalls. So now we are only looking at 1 stall. So this was done by just swapping the branch instruction and the store and by changing the address of store. Because the sub instruction already modifies the value of R1, when you execute the store instruction, it will do a wrong store. So in order to compensate for whatever the sub instruction has carried out, you find that the store instruction does not store into 0 R1, it now stores into 8 R1 because the sub instruction has already reduced R1 by 8. So that compensation has been carried out. So with just a simple way of modifying the address in your store instruction and doing a reorganization of the code, we find that we were able to get a better schedule compared to the original schedule that you had. So this is the first compiler technique that we are looking at. So reorganizing the code will definitely lead to a better schedule. So now we have only 6 clock cycles to execute this loop as against 10 clock cycles that we discussed earlier. Now we will introduce a second concept, the compiler related concept. Just like how we did a dynamic unrolling of the loop in the dynamic scheduler with a dynamic branch predictor, now we have a static branch predictor. So the compiler in these simple iterative loops, it can easily predict that the branch is going to be taken. So you do a static prediction, and based on the static prediction, you do an unrolling of the loop. So we do a static unrolling of the loop. So static unrolling of the loop is nothing but replicating the loop. So this shows the loop unrolling process that happens. So loop unrolling process that has happened, and simply just arranging it in that same order without doing any extra rescheduling. So if you look at these instructions, what is the concept of loop unrolling is, so I have a load instruction. Following that, because it's a dependent add, I have a stall, and then I have the add instruction. I have 2 stalls, then I have the store instruction. Look at the fact that the loop unrolling process has simply replicated the loop. Because the loop has got replicated, you don't have to bring in the loop maintenance code. See, after all, what the loop maintenance code did was modifying the R1 register so that it will point to the next location in memory, and the branch instruction which checked whether you will have to keep continuing iterating the loop or come out of the loop. Now, whatever R1 value, modified value the sub instruction did, we are incorporating it into the second load instruction itself. As you can see, the second load instruction loads not just from 0 R1, then it will load the same value. It is loading from minus 8 R1. So, whatever our subtract instruction of R1 did, we are able to incorporate that into our load instruction itself. That is one observation that you will have to make. The second observation that you will have to make is, you are not using the same register F0 here, you are using a different register called F6. So, that is the register renaming process that happens. So, when you are doing a loop unrolling process, you will have to take into account all this. The basic idea is, when you are doing a loop unrolling process, you are replicating the loop in order to get more number of independent or parallel instructions. When will instructions become parallel or independent? Only when they do not have any dependencies. So, name dependencies also will have to be resolved. There should only be data dependencies, and data dependencies, if you are not able to reschedule them, then you will have to introduce stalls. So, the name dependencies are resolved by using a different register here. So, the second set of instructions uses a different register, for example F6, it uses a different address minus 8 R1. If you look at the third iteration, it uses a different address as minus 16 R1, it uses a different register F10, and if you look at the fourth iteration, it uses a register F14, and you find that the address is minus 24 R1. And similarly, when you look at the add instruction also, the destination register of the add instruction is not the same. It is F4 in the first iteration, it is F8 in the second iteration, it is F12 in the third iteration, and it is F16 in the fourth iteration. So, because we have replicated the loop 4 times, observe the fact that we have removed all the loop maintenance code here, but at the end of the loop it may have to be executed more number of times. So, the loop maintenance code comes towards the end. So, the subtract instruction uses a value of minus 32. We have already handled 0, minus 8, minus 16 and minus 24. So, the next data will have to be fetched from minus 32 R1. So, that is what is given in your subtract instruction, and of course, you have a branch. So, with 4 unrolls of the loop maintenance code which was available in every iteration of the loop has been removed, and it has been incorporated only in the last iteration. So, this is the concept of loop unrolling. So, you are replicating the loop enough number of times. So, replication, remember that you will have to remove all the name dependencies, and you will also have to adjust the addresses appropriately. So, this loop unrolling of 4 times takes about 28 clock cycles for execution or 7 clock cycles per iteration. Remember that we have not done any reorganization of the code, we have not tried to schedule the instructions appropriately, we have just done a loop unrolling process, and we are just assuming that R1 is a multiple of 4. So, now what we are trying to do is, we are also trying to bring in the other optimization of appropriately scheduling the instructions, so that the stalls that were introduced between dependent instructions can also be filled up with independent instructions. So, if you recall the previous schedule, we had a load, and following add, because it was a dependent add, we had to introduce a stall now. So, now what we are trying to do is, we are doing a rescheduling of the instructions. All the loads, for example, have been brought together. These loads are totally independent of each other, so they can happen in parallel, and then you have all the adds coming into picture. So, the latency between your load 1 and add 1 is satisfied. You have 3 clock cycle latency here. Similarly, between your add and store, we had to have 2 latencies, that is also being taken care of. And in order to account for the last data dependency between your sub instruction and the branch instruction, you find that the last store instruction has been brought to the end, and the sub instruction has been moved ahead. The store instruction has been brought in there, so that you are able to handle all of this. And the store address has been appropriately modified, because your sub instruction has been moved earlier, then you know that the sub instruction will modify the store address. So, that has been appropriately taken care of by the last store instruction. So, this is the concept where you are not just unrolling the loop, but you are also scheduling it appropriately, so that stalls get minimized. So, what are the assumptions that we have made when we move this code? So, we assume that it is okay to move the store instruction past the sub instruction, even though it changes the register. And the second thing is, we have identified the fact that it is okay to move the loads before the stores, and we know that it will get the right data. And it will also have to look at the fact that when is it safe for the compiler to do such changes. So, we will have to make sure that these are not referring to the same addresses. So, only if they do not refer to the same effective addresses, you can do changes of these loads and stores. You can shift these loads and stores as wherever you want. So, in this case we have only 14 clock cycles or 3.5 clock cycles per iteration. So, normally when you look at a loop unrolling process, so we do not know how many times the loop will have to be executed. So, suppose it is a n and we would like to unroll the loop to make k copies of the body. If you have to unroll the loop 100 times, obviously it is not possible to unroll the loop 100 times. You have other constraints that will come in. You may not be able to replicate it 100 times. So, let us assume that we are replicating the loop k times. So, instead of a single unrolled loop, uh, what we have here is, earlier we had a single rolled loop. Now we can't have a single unrolled loop. We just have two loops. So, we have two consecutive loops. So, the first loop executes n mod k times, and it is the original loop, which is the rolled loop. The second one is the unrolled body surrounded by an outer loop that iterates n by k times. Say for example, if you have to execute the loop 100 times, and let me say I am able to unroll the loop 6 times. So, which means I will have an unrolled loop, a loop which has been unrolled 6 times, and that will get executed 16 times. So, 16 into 6, 96 times the unrolled loop will get executed, and the remaining 4 times 100 mod 16, the remaining 4 times the original loop will get executed. So, for large values of n, most of the execution time will be spent only on the unrolled loop. So, you will get the benefit of unrolling. So, the points that you will have to remember with loop unrolling are, you will have to determine that it was okay or legal to move the store instruction after the sub instruction and branch, and find the amount that you have to adjust in your store offset. You also have to determine that unrolling the loop would be useful by finding that the loop iterations were independent of each other. So, if there is a loop carry dependence, you can't do that. So, except for the loop maintenance code, you are trying to do the unrolling of the loop. And use different registers to avoid unnecessary constraints that would be forced by using the same registers for different computations. Obviously, you will have to avoid all the name dependencies and eliminate the extra tests and branches and adjust the loop maintenance code accordingly. Remember that because we unrolled the loop 4 times, 3 iterations of the loop did not have any loop maintenance code, only the last iteration had the loop maintenance code. And determine that the loads and stores in the unrolled loop can be interchanged by observing that the loads and stores from different iterations are independent of each other. This requires the analysis of the memory addresses and finding that they do not refer to the same address. And of course, finally, schedule the code, preserving any dependencies needed to yield the same result as the original code. Of course, you have certain limits to loop unrolling. One is, as Amdahl's law says, it is a law of diminishing returns. So, there is a decrease in the amount of overhead that is amortized with each extra unrolling. So, the benefits that you get out of each unroll may not be the same as we got earlier. The second one is the growth in code size. Obviously, when you are replicating the code size increases enormously. When you are replicating it 4 times, obviously it sort of increases 4 times. So, when the code size increases too much, it is possible that it might lead to a cache miss, and you may have the effects of unrolling being nullified by this. So, you will have to be careful about the growth size. The third limitation to loop unrolling is the register pressure. Because there are only limited number of registers available in the processor, you may not have enough registers that can be used for unrolling, because name dependencies, you know, you will have to look at bringing in different registers. So, register pressure may not allow you to do enough loop unrolling. So, loop unrolling reduces the impact of branches on a pipeline because you know that you are removing all the loop maintenance code. So, another way is, of course, you know, it is a branch prediction. You do a static branch prediction, and based on that you do a loop unrolling, and you are also going to remove all the loop maintenance code. The compiler perspectives on code movement. We've already looked at in an earlier modules in the beginning, we've already looked at dependencies. You know that dependencies are properties of programs which the compiler is worried about, and hazards, whether these dependencies will turn out to be hazards, depends on how these instructions are executed in the pipeline. So, dependencies are always there, dependencies are properties of programs. Whether these dependencies will turn out to be hazards will depend on how they get executed in the program, and the compiler will try to schedule them so that you do not have problems with these dependencies. Now, data dependencies will give rise to what are called raw hazards. So, if data dependencies are not handled properly, so if the compiler does not try to do a reorganization of code, then it will be limited by means of the data dependencies. You cannot avoid data dependencies. So, true data dependencies will definitely give rise to a raw hazard. So, how the compiler tries to organize them, remove the data dependence, or remove the problem that a data dependence may cause, is by trying to do a reorganization of the code. So, it will try to bring in an independent instruction between the two dependent instructions. And as far as name dependencies are concerned, you can do a register renaming process. Now, identifying these dependencies obviously becomes very difficult for memory. How do you know whether a 32R4 and a 20R6 refer to the same effective address or not? So, if you calculate the effective address, you will know that they are going to refer to the same memory location. So, if they refer to the same memory location, it is not possible for you to not follow the program order. So, if you look at name dependencies as you all know can be caused by anti-dependence and output dependence, and if they are not handled properly, they will give rise to a war hazard and a war hazard. So, the compiler is worried about name dependencies. So, for example, here you find that if you are using the same register, then it will give rise to a name dependence. The first load instruction also writes into F0, the second load instruction also, if it writes into F0, that will give rise to a name dependence, it will give rise to a war hazard, which is not allowed. So, what we do is where we do a renaming process, instead of using an F0, we use a different register, thus removing the name dependence associated with these two instructions and avoiding the war hazard. So, again, name dependencies are hard for memory accesses. So, how do we know that these two memory locations refer to the same? So, in that case, you will have to calculate these addresses and then check whether these addresses refer to the same effective addresses. Only then you will have to decide whether it is possible to shift them around or not. So, in our example, the compiler had to find out that 0R1, minus 8R1, minus 16R1 and minus 24R1 refer to different effective addresses because R1 does not change. So, there were no dependencies between these addresses, they are different addresses. So, it was possible for us to reorganize our load and store instructions. And final kind of dependence, of course, is the control dependence, where you have a branch instruction, and you know that if an instruction is control dependent on P1 and another instruction S2 is control dependent on P2 but not on P1, you will have to maintain the control dependence. You can't reorganize the code in such a way that the data flow is affected and also the exception behavior is affected. So, the control dependence, we are only bothered about changing the instructions based on a branch. If you do a reorganization of the code, it should not affect the data flow, and at the same time you should also preserve the exception behavior. So, all this will have to be taken care of when you have to look at handling control dependence. So, as long as you are able to maintain the data flow and as long as you are able to preserve the exception behavior, you are allowed to move instructions around the branch. So, here the control dependencies, the sub instruction, you have your sub instruction which generates a value for R1 and the branch instruction gives rise to a control dependence. So, if you want to move the sub instruction or a load instruction there into the branch, then you have this reorganization might give rise to a problem, data flow problem. So, that will have to be appropriately handled by adjusting the store address. And of course, when you are removing the loop maintenance code, you are also removing the control dependencies. So, that is obviously an advantage associated with your loop unrolling process. Now, when can we actually unroll loops? When is it safe to unroll loops? In the earlier case, when we looked at an iterative loop, each iteration of the loop was clearly independent of each other. You were able to unroll the loop. But now look at as two examples that have been given here. So ai plus 1 is dependent on ai. So the I plus 1th iteration is dependent on the ith iteration. Similarly, bi plus 1 is equal to bi plus something. So you have bi plus 1 again dependent on bi. So this gives a case of a loop carried dependence. In both these cases, you have a loop carried dependence between iterations. So unless iteration 1 finishes, you can't execute iteration 2. So there is a loop carried dependence between iterations. So in such cases, loop unrolling cannot be done effectively. Unless of course you are able to do something and remove the loop carried dependence, you cannot do a loop unrolling process straight away. So an easy target for loop unrolling process is iterative loops which don't have a loop carried dependence. Earlier case, that was the case. We did not have a loop carried dependence, so we were able to easily unroll the loops. So basically how the compilers can be smart is to find out that loops might contain parallelism. So they don't have a loop carried dependence, independent iterations of the loops. So it is possible for them to be unrolled. So while unrolling the loop, take care of all the precautions that you will have to do. Make sure that you remove all the name dependencies by using different registers. Make sure that you remove all the loop maintenance code and appropriately include the loop maintenance code at the end of the iteration. Make any changes to the addresses that the loop maintenance code would have brought in, because you are removing the loop maintenance code. And of course, just unrolling the process alone will not be enough. You will also have to do a proper scheduling of the code in order to get a stall-free schedule. So to summarize, we've identified the fact that it is not just the hardware that can exploit instruction level parallelism. So the compiler also can exploit instruction level parallelism. An easy target for compilers to exploit the instruction level parallelism are iterations without a loop carried dependence. And loop unrolling is a very common way of exploiting ILP, where a loop simply gets, iterations of the loop simply get replicated. And when you are doing the replication, you have to take care of different things. Basically, the idea is to generate enough number of parallel instructions. So instructions can be parallel only when they don't have any dependencies. So all name dependencies will have to be resolved by doing a register renaming process. And control dependencies are basically handled by means of static prediction. And in most of the unrolls, the control dependence itself is getting removed because you are removing the loop maintenance code. And there are still other techniques that we will be looking in the next module. In this module, we only looked at loop unrolling as a compiler related technique, and of course scheduling, doing a static schedule by reorganizing the code. So these were the two techniques that we discussed in this module. So the next module, we will also look at some other techniques which are used by the compiler, it is software approaches for exploiting instruction level parallelism. Thank you.